A cosmic wheel of fire spins 500 million light-years away. This is the Cartwheel Galaxy, a celestial oddity so strange it looks like a stone was thrown through a pond of stars. By the end of this journey, you will know 25 of its most baffling secrets, each one a piece of a puzzle that rewrites the rules of galactic life. We will find mysterious spokes in the wheel, X-ray sources brighter than physics allows, and ghostly companions locked in a gravitational dance. What does a perfect cosmic crash teach us about our own galaxy's violent past? The Cartwheel Galaxy did not always spin in this perfect ring of fire. Its story begins with a cosmic catastrophe of almost unimaginable violence. Astronomers believe the galaxy was once a normal, placid spiral, much like our own Milky Way quietly tending its stars. Then a smaller galaxy, likely one of its own companions, plunged directly through its heart at staggering speeds. This was not a glancing blow, but a head-on, high-speed collision, a celestial bullseye. The effect was like dropping a stone into a still pond of stars and gas, sending colossal shockwaves rippling outward at millions of miles per hour. These waves compressed the galaxy's gas, triggering a frenzy of new starbirth that lit up in a brilliant, expanding ring. That ring is what we see today, the glowing rim of the cosmic wheel. The galaxy's old core was left behind, displaced and off-center, a silent witness to the impact. You can see this in images, the bright, dense knot of older stars sitting not in the middle of the ring, but noticeably to one side, like the hub of a wheel that has been violently shoved aside. This single, violent event set the stage for every other strangeness we find there, a reminder that in the cosmos, creation and destruction are often the same force, sculpting beauty from chaos. That brilliant outer ring is not floating freely in space. It is tethered to the galaxy's displaced heart by a series of faint, radial filaments that astronomers call the spokes. These are the galaxy's secret architecture, the ghostly scaffolding holding this cosmic wheel together. Picture the thin, straight lines you see connecting the hub to the rim of a bicycle wheel. In the cartwheel, these are not solid rods, but vast lanes of dust, gas, and incredibly young, hot stars, all stretched out over tens of thousands of light-years. Their very existence is a profound puzzle. You would think the titanic shockwave from the collision would have blasted everything into a smooth, symmetrical ring. Yet here these delicate structures persist, cutting straight across the chaos. So what are they? One leading theory is that they are fossilized traces of the original impact, like the lingering grooves in a record of that ancient violence. As the shockwave expanded, it may have left behind these denser trails where star formation was triggered a little earlier or a little more intensely. Another idea points to the invisible hand of magnetic fields. The collision would have scrambled and amplified the galaxy's magnetic forces, potentially channeling gas and dust into these long, straight rivers that then birthed new stars. Their persistence is just as mysterious. These spokes should be unstable, dissolving and twisting under the immense gravitational forces at play. The fact they remain so straight and distinct suggests some continuous process, perhaps ongoing star formation or magnetic reinforcement, is actively maintaining them. They are a silent blueprint, a lasting signature of the catastrophe that built this galaxy, and understanding their true nature is key to deciphering the entire structure. These mysterious spokes lead our eyes toward points of even greater intensity, hidden within the ring's glow. Scattered across the cartwheel star-forming rim are several pinpricks of energy so fierce they blaze not in visible light but in X-rays. Astronomers call them ultra-luminous X-ray sources, or ULXS. To understand why they are so baffling, we need to grasp a basic cosmic rule. A typical black hole formed from a collapsing star, what we call a stellar mass black hole, has a maximum brightness it can achieve as it pulls in material, a limit set by fundamental physics. Yet these ULXS in the Cartwheel shine hundreds, even thousands of times brighter than that theoretical limit. They are far too luminous to be explained by a normal stellar black hole, yet they are also not located in the galactic center and are not nearly as bright as the supermassive black holes that power entire galaxies. So what are we looking at? Each one is a point-like beacon of extreme violence, defying simple classification. One compelling theory is that they are intermediate mass black holes, elusive cosmic objects with masses between a few hundred and a few 100,000 times that of our Sun. These would be the missing link between small stellar black holes and the galactic giants, and finding them here in the wreckage of a collision would be a monumental discovery. Another possibility is that we are seeing stellar black holes in a state of extreme and gluttonous feeding, pulling in gas so rapidly that their radiation punches through the usual brightness limits in a way we do not fully understand. Or perhaps they are something else entirely, like exotic neutron stars with unimaginably powerful magnetic fields. Their very presence in the Cartwheel tells us this galaxy is not just a beautiful ruin. It is a laboratory for the most extreme physics, where the chaos of the collision created perfect conditions for spawning cosmic anomalies that challenge our textbooks. This ferocious star formation paints the Cartwheel's outer ring in a brilliant electric blue, a color that in the cosmos screams youth, heat, and violence. We are looking at one of the most intense starburst regions known, a ring of fire where the galaxy is giving birth to stars at a rate that utterly dwarfs our own quiet celestial neighborhood. To grasp the scale, consider the Milky Way. Our galaxy is mature and relatively settled, forming about one new star per year on average. The Cartwheel's ring, by contrast, is a stellar nursery in overdrive, creating new suns at a rate hundreds of times faster. The shockwave from the ancient collision did not just push gas outward, it crushed it. Imagine a cosmic tsunami sweeping through a cloud, compressing the hydrogen and helium within to incredible densities. In those dense, turbulent pockets, gravity takes over, pulling the gas into collapsing knots that ignite into newborn stars. The result is not a gentle sprinkling of new lights, but a firestorm of creation. Within that glowing blue ring, you are seeing not individual stars, but vast clusters of them, each cluster containing thousands or even millions of stellar infants. These are not stars like our stable, middle-aged sun. They are monsters born with many times the sun's mass, blazing with a fierce blue-white intensity. Their lives are spectacularly short and explosive. A star like our sun can burn steadily for 10 billion years. These massive stars in the Cartwheel's ring live fast and die young, exhausting their nuclear fuel in just a few million years. Their deaths are not quiet. They end as colossal supernova, explosions that rip them apart and blast newly forged heavy elements like carbon, oxygen, and iron back into the surrounding gas. This enriched material then gets swept up into the next generation of stars and planets. So this ring of fire is more than just a beautiful aftermath. It is a cosmic engine for recycling and enrichment, forging the very building blocks for future rocky worlds and potentially life itself in its furious crucible. But the Cartwheel does not spin in solitary silence. It is the centerpiece of a small, dramatic group, flanked by two smaller, ghostly companion galaxies. These cosmic partners hold the key to the entire mystery, for one of them is almost certainly the intruder that shattered the Cartwheel's peaceful past. Yet identifying the culprit is not as simple as pointing to the nearest suspect. Both companions show the scars of a tremendous gravitational brawl. Their shapes are distorted, stretched and pulled out of their original spiral forms by the same forces that created the ring. Long, faint streams of stars and gas, called tidal tails, arc away from them like cosmic cobwebs. These tails are the gravitational signatures of a close encounter, material ripped from the galaxies as they grazed or passed through one another. It is as if we have arrived at the scene of a collision and found two damaged vehicles, each bearing the marks of impact, so which one actually struck the fatal blow? The larger of the two companions, often called Galaxy G1, shows clearer evidence of a recent direct interaction, its structure heavily disrupted. Many astronomers point to it as the prime suspect, the bullet that shot through the Cartwheel's heart. The smaller companion may have been a bystander caught in the gravitational chaos, or perhaps it interacted earlier in a complex three-body dance. This uncertainty adds a layer of detective work to the cosmic crime scene. More importantly, it raises a profound question about the galaxy's future. Is the Cartwheel story a finished chapter, a beautiful monument to a single ancient crash, or are we looking at a snapshot of an ongoing celestial ballet? The gravitational pull between these galaxies is immense and unbroken. They are still connected by those faint tidal streams, invisible threads of force that continue to tug and influence one another. The companions may be slowly falling back toward the Cartwheel for another encounter, or they may be destined to forever orbit their wounded giant, their shapes perpetually molded by its gravity. This means the Cartwheel is not a static painting, but a living, evolving system. The same forces that built its ring of fire are still at work, quietly scripting the next act in a saga that unfolds over billions of years. All that furious starbirth should be screaming across the radio spectrum, yet the Cartwheel Galaxy whispers instead. This is the strange case of the missing radio emission. In a galaxy churning out hundreds of new stars every year, we expect a corresponding roar of radio waves, a signature created by two things. The first is synchrotron radiation, generated by cosmic ray electrons spiraling at near light speed through the galaxy's magnetic fields. The second is thermal radiation from the hot ionized gas around all those massive young stars. Standard models, built from observing other starburst galaxies, tell us exactly how loud this radio roar should be for a given rate of star formation. But when astronomers pointed radio telescopes at the Cartwheel, the signal was far weaker than predicted. It is as if you walked into a packed, roaring stadium and heard only the murmur of a quiet conversation. So what is silencing the cosmic noise? One compelling clue points to the galaxy's unique magnetic architecture. Those mysterious spokes we discussed earlier might be key. If the magnetic fields within the Cartwheel are highly ordered and straight, aligned along those radial spokes rather than tangled and chaotic, cosmic ray electrons could be streaming out of the galaxy along these magnetic highways like cars on a freeway. Instead of getting trapped and spiraling violently to produce intense radio waves, they are efficiently escaping into intergalactic space, taking their energy with them. Another possibility involves the cosmic rays themselves. Perhaps the extreme conditions in the ring's supernova are producing a different population of particles, or maybe the sheer density of the gas is somehow suppressing their ability to generate the expected signal. This quiet discrepancy is more than a minor technicality. It is a direct challenge to our understanding of the fundamental physics linking star formation, magnetic fields, and particle acceleration. The Cartwheel is showing us that the cosmic rulebook we have written from studying more normal galaxies may be incomplete, or that in the aftermath of a colossal collision, the universe operates by a subtly different set of instructions. The galaxy's quiet radio whisper is not its only chemical mystery. When astronomers peer deeper, using the precise tool of spectroscopy to dissect the light from its brilliant ring, they uncover a recipe that does not quite match the cosmic cookbook. The starburst ring is a chemical factory, forging new elements in the hearts of its massive stars and blasting them into space through supernova. By analyzing the specific colors or spectral lines of light emitted by the glowing gas, scientists can determine exactly which elements are present and in what amounts. Here, the Cartwheel presents another puzzle. The ratios of certain key elements, like oxygen to nitrogen, are off. They do not align with what we typically measure in other intense star-forming regions across the universe. It is as if you followed a familiar cake recipe, but the final flavor was unexpectedly different, hinting at an unknown ingredient or a changed step in the process. This chemical fingerprint is a powerful clue, a historical record written in atomic light. The unusual abundances suggest that the star formation here did not follow a simple, single script. Perhaps it was not one giant burst triggered by the initial collision, but a series of waves. An initial wave of supernova would have enriched the ring's gas with a specific blend of elements. Then, as the shockwave continued to move and compress material, later generations of stars would have formed from this already altered fuel, creating a new chemical signature. Alternatively, the unique violence of the head-on collision itself may have mixed the galaxy's ingredients in an unprecedented way, stirring the primordial gas from the outer regions with whatever was already in the galactic core, creating a novel chemical soup for starbirth. This strange elemental ratio is more than a curious detail. It is a direct window into the timeline of the catastrophe, helping astronomers piece together whether the ring of fire ignited in a single brilliant flash or in a sustained, rolling series of explosions that reshaped the galaxy's very composition. While the outer ring screams with newborn stars, the galaxy's inner region tells a quieter, more ancient story. This area, nestled between the brilliant rim and the displaced core, is a zone of transition and lingering mystery. Here, the shockwave's fury has passed, leaving behind a landscape that is neither the frenzied nursery of the ring nor the dense old heart of the galaxy. It is a place of aftermath where the gas has been largely swept away or used up, revealing an older population of stars that date back to before the Great Collision. These stars are the silent survivors, witnesses to the catastrophe that reshaped their home. Their light is redder and calmer than the blue giants in the ring, signifying their advanced age and lower mass. Studying this inner region is like examining the quieter neighborhoods of a city after a massive reconstruction project downtown. It holds clues to what the original galactic structure was like before everything changed. But the most compelling mystery in this inner zone lies at its very heart, or rather, where the heart should be. The galaxy's original core, a dense knot of billions of stars, is not centered within the ring. It sits noticeably off to one side, a hub knocked askew. This displacement is the ultimate proof of the collision's direct hit. When the smaller galaxy bulleted through, its gravity did not just send ripples outward, it delivered a colossal kick to the cartwheel's very center of mass, shoving it off its axis. Think of it like striking a bell not perfectly in the center. The whole structure vibrates and the clapper is thrown off balance. So what became of this displaced core? Observations show it is predominantly composed of those older, redder stars, a retirement community for stellar populations that formed in the galaxy's youth, long before the Ring of Fire existed. Yet there is a lingering question about its supermassive black hole. Nearly every large galaxy harbors one of these gravitational monsters at its center. Given the galactic drama unfolding just outside, with rampant star formation and stellar explosions, you might expect the Cartwheel's central black hole to be feasting on any gas funneled inward, lighting up as a brilliant active galactic nucleus. But it remains surprisingly, profoundly quiet. This quiescence is a puzzle. Did the collision strip away the gas and dust it needed to feed, starving it into silence? Or is the activity simply hidden, its energy channeled in ways we cannot yet detect? The quiet core, sitting off-center amidst the stellar storm, is a reminder that the collision's impact was not just creative, it was also deeply disruptive, leaving even the galaxy's most powerful engine seemingly dormant. The raw fuel for all this stellar fire is something far colder and darker: giant molecular clouds. These are the cosmic nurseries, vast and frigid structures of gas and dust so dense that molecules like hydrogen can form within their shadowy hearts. In a calm galaxy like our own, these clouds drift slowly, collapsing over millions of years under their own gravity to birth clusters of stars. But in the Cartwheel, nothing is calm. The collision's shockwave did not just push these clouds, it violently compressed them, turning serene stellar nurseries into pressure cookers of creation. The clouds here are not just large, they are monstrous, containing the mass of millions of suns and existing under conditions of extreme pressure unseen in more tranquil galactic neighborhoods. This extreme environment forces them to behave in profoundly strange ways. One possibility is that they are collapsing with terrifying speed and efficiency. The immense external pressure from the shockwave might be overwhelming the cloud's own internal support, gravity gaining a decisive upper hand and triggering star formation on a scale and at a pace that breaks all local records. It is starbirth as a stampede, not a slow procession, but there is another, more violent fate. The same titanic forces that compress these clouds also exert incredible tidal stresses, gravitational shearing forces that can stretch and tear structures apart. Imagine trying to form a snowball while standing in a hurricane. The material is there, but the environment is actively working against its cohesion. Some of these giant molecular clouds in the Cartwheel may be caught in this exact struggle, simultaneously being squeezed into collapse and ripped apart by the galaxy's fierce dynamics. We might be witnessing clouds that are forming stars even as they are being shredded, a chaotic and inefficient process that scatters their material back into the ring. Which of these opposing destinies dominates? The answer could rewrite our understanding of how stars are forged in the universe's most extreme environments, revealing whether such colossal collisions are master builders or cosmic wrecking balls at the most fundamental level. The intense starlight from the ring does more than paint the galaxy blue. It heats up a hidden component of the cosmos. Across the entire Cartwheel, from its brilliant rim to its quieter inner regions, a pervasive, diffuse infrared glow blankets everything. This is not the sharp, pinpoint light of stars or the fierce glare of those ultra-luminous X-ray sources. This is a soft, all-encompassing warmth, the thermal signature of countless microscopic dust grains that have been gently heated by starlight. In most galaxies, this dust is concentrated in star-forming clouds and along spiral arms. Here, it is everywhere. The collision acted like a cosmic sandstorm, blasting tiny particles of silicon, carbon, and ice far from their original homes and spreading them across an immense volume of space. The sheer scale and uniformity of this infrared glow is a direct measure of the impact's violence. It suggests that the force of the encounter did not just compress gas to make stars, it also took solid material, the building blocks of future rocky planets, and hurled it far and wide, perhaps even launching a significant fraction of it on a one-way trip into the cold emptiness between galaxies. This faint, warm haze is therefore a ghostly map. It traces the paths of ejected material, showing us how far the shockwaves truly reached and how thoroughly the galaxy's very substance was scrambled. It is a reminder that a galactic collision is not a clean event. It is a messy, scattering affair that can leave a permanent, dusty fingerprint on the void itself. This faint infrared haze is a sign of material thrown into chaos, and that chaos is still in motion. To see it, astronomers use a fundamental tool of cosmic detective work, the Doppler shift. Just as the pitch of a siren rises as an ambulance races toward you and falls as it speeds away, the light from moving gas in space gets subtly shifted in color. Gas moving toward us is squeezed, its light shifted toward the blue end of the spectrum. Gas rushing away is stretched, its light reddened. By meticulously measuring these tiny color shifts across the Cartwheel's brilliant ring, scientists can map its hidden currents and flows. What they find is not a simple, orderly wheel spinning in the void. The motion is a turbulent mess. Instead of a clean, circular rotation, the gas shows complex, chaotic patterns. Some streams race inward, funneling material back toward the galaxy's displaced heart. Other currents surge outward, as if the ring itself is still expanding from that ancient shockwave. There are whirlpools and eddies within the larger structure, areas where the gas seems to churn in place or flow in directions that defy a simple orbit. This is the direct fingerprint of a system still recovering from a catastrophic blow. Picture a vast pond moments after a boulder has crashed into its center. The main circular wave expands outward, but the water within that wave does not move in a perfect ring. It sloshes, it churns, it flows backward in some places and forward in others, a turbulent interplay of momentum and gravity. The Cartwheel's ring is that pond, but on a scale of hundreds of thousands of light years, and the splash happened hundreds of millions of years ago. The fact that this sloshing motion persists tells us the galaxy has not yet settled into a new equilibrium. The colossal impact set its substance into a state of prolonged agitation, and the echoes of that violence are still playing out in the frantic dance of its gas. This peculiar motion is more than just a curiosity. It dictates the galaxy's future. Those inward flows could be feeding the quiet core, perhaps setting the stage for its dormant black hole to one day awaken. The outward surges might be how the galaxy loses its star-forming fuel forever, slowly bleeding the raw material for new suns into the intergalactic void. Within that churning sea of blue starlight, the Cartwheel's ring holds concentrated points of brilliance so intense they defy ordinary scale. Astronomers call them candidate superstar clusters, and each one is a city of stars, a single, gravitationally bound metropolis containing the mass of millions of suns packed into a space only a few dozen light years across. To grasp their density, imagine squeezing all the stars from our entire local galactic neighborhood into a volume so small you could cross it in a cosmic heartbeat. These are not mere open clusters like the Pleiades. They are the potential infant versions of the most ancient and massive star systems we know, globular clusters. Globular clusters are typically fossils from a galaxy's violent infancy, ancient balls of hundreds of thousands of stars that orbit the galactic core like distant, loyal satellites. We see them around the Milky Way, but they are all billions of years old, their stories of formation long concluded. In the Cartwheel, we are witnessing that same extreme process of cluster birth happening right now, in an explosive flash of creation triggered by the collision. The shockwave provided the perfect recipe, compressing gas clouds of unimaginable size and density into knots so tight that gravity could pull them into a single, monstrous collapse, igniting not just a few stars, but a whole stellar civilization at once. This gives us a rare, real-time laboratory to watch how the universe builds its most colossal star clusters. We see them blazing with the fierce light of countless massive, short-lived stars, their combined ultraviolet radiation carving out vast cavities in the surrounding gas. Their future is a cosmic question. Will they survive the coming millennia? The supernova explosions from their most massive members will be apocalyptic, ripping through the cluster with enough force to potentially blow it apart from within. Only the clusters with the deepest gravitational wells, those that formed with enough mass to hold onto their stars through the stellar chaos, will endure. The survivors will slowly eject their lighter stars, tighten their bonds, and over billions of years, evolve into the dense, spherical globular clusters that will orbit the Cartwheel's future generations. These brilliant points of light are therefore both a beginning and an end, the explosive birth cries of structures meant to last for the lifetime of the galaxy itself. The brilliant chaos of the Cartwheel's ring is held in check by an invisible hand. The frantic motion of its stars and gas, that turbulent sloshing we just explored, reveals a profound truth. The gravity required to keep this entire spinning wreck from flying apart is far greater than the pull we can account for from all its visible stars, gas, and dust combined. The missing force points to a massive, shadowy presence, a vast halo of dark matter enveloping the galaxy. This mysterious substance, which does not emit, absorb, or reflect light, reveals itself only through its immense gravitational grip. Every large galaxy is believed to be embedded in such a halo, an invisible scaffold of unknown particles that forms the true backbone of cosmic structure. But here, in the aftermath of a head-on collision, a strange new question emerges. How does dark matter behave in a cosmic crash? When the smaller galaxy bulleted through the Cartwheel's heart, what happened to its invisible halo? The visible stars and gas were violently compressed and scattered, creating the ring of fire. Dark matter, however, is thought to be collisionless. Unlike atoms that smash together, dark matter particles would simply pass through each other and through the normal matter, feeling only gravity's pull. This means the collision might have been a very different event for the dark halos. One leading idea is that the halos of the two galaxies, like vast, ghostly clouds, simply passed through one another with barely a ripple, while their visible contents smashed together in a spectacular display. If true, the Cartwheel's dark matter halo could remain largely intact and spherical, a silent, unmoved anchor around which the visible wreckage now orbits. This could be the key to the galaxy's surprising long-term stability. That intact dark matter scaffold provides the deep, steady gravitational well that keeps all the churning, expanding visible material from simply drifting away into the void. It is the cosmic glue holding this beautiful ruin together. Yet, other simulations suggest the gravitational interaction alone, even without direct collisions, could have stretched and distorted the dark matter halos, pulling them out of shape into elongated streams or leaving wakes of invisible material. The true distribution of dark matter in the Cartwheel remains one of its deepest mysteries, a hidden map that would tell us not just about this galaxy's fate, but about the fundamental nature of the universe's most abundant yet elusive substance. Even the galaxy's most brilliant stars are not steady beacons. When astronomers watch the Cartwheel over months and years, a practice called time-domain astronomy, they catch a subtle, flickering light show scattered across its face. These are variable objects, sources that rhythmically brighten and dim or flare unpredictably. Many types of variable stars are well understood, like pulsating giants that swell and shrink, or binary pairs where one star eclipses the other. Yet within the Cartwheel's chaotic landscape, some of these flickering points refuse to fit into our familiar cosmic catalogue. Their patterns of light are strange, their rhythms unfamiliar. One might pulse with a tempo that suggests a new, extreme class of pulsating star, one born from the unique pressures of the starburst ring. Another might flare with the sudden, violent intensity of a rare binary interaction, perhaps a dense neutron star stripping material from a companion in fits and starts. The most tantalizing flickers could be brief, furious accretion events, where a clump of gas finally spirals into a black hole or neutron star, releasing a flash of energy that winks into view and then vanishes. Each unidentified variable source is a small, persistent mystery. It is a signal without a clear sender, a behavior that challenges our classification systems. In a galaxy built from a collision, perhaps even the stars themselves pulsate to a different, more chaotic beat, their inner workings altered by the violence of their birth. Solving these small mysteries, one flicker at a time, is how we slowly learn the new rules of physics written in the aftermath of cosmic chaos. The flickering stars are not the only clues written in light. To see the galaxy's most ferocious stellar newborns, we must look beyond the visible spectrum into the searing glare of ultraviolet light. This high-energy radiation is the exclusive signature of the hottest, most massive stars, stellar behemoths that live fast and die young, bathing their surroundings in an intense ultraviolet glow. When space telescopes like Hubble map the Cartwheel in ultraviolet, they reveal a skeleton of star formation, tracing the bones of the starburst ring in exquisite detail. But the picture they paint is unexpectedly uneven. Instead of a smooth, uniform band of ultraviolet light, the ring breaks apart into a string of brilliant, isolated knots and patches, separated by darker, quieter gaps. Astronomers call these ultraviolet hotspots, and their patchy distribution is a puzzle. If the initial shockwave from the collision expanded outward as a perfect, symmetrical ring, you might expect it to trigger star formation evenly, like a ripple igniting a continuous fuse. The reality is a broken necklace of stellar fire, with some segments blazing fiercely and others strangely subdued. This irregularity is a vital clue, a frozen snapshot of how the wave of creation actually traveled. Think of the shockwave not as a smooth wall of water, but as a tsunami encountering a complex coastline. As it expanded through the Cartwheel's pre-existing gas, it would have encountered regions of varying density. In areas where the galactic gas was already thick and lumpy, the wave compressed it catastrophically, triggering an immediate and furious burst of star formation that shines brightly in ultraviolet. In places where the gas was thinner or more smoothly distributed, the wave might have passed through with less dramatic effect, leaving behind a fainter glow or even skipping star formation entirely. The pattern of hotspots, therefore, is a direct map of the galaxy's internal structure from hundreds of millions of years ago. It tells us the pre-collision cartwheel was not a featureless disk of gas, but a textured and uneven landscape, and that the violence of the impact sculpted that landscape into a discontinuous ring of fire. The galaxy's quiet core holds a deeper secret than its current slumber. While its central supermassive black hole appears dormant today, astronomers are hunting for the ghostly echoes of a more violent past. They are searching for fossil evidence in the faint whispers of X-ray and radio data, looking for structures that would prove this sleeping giant was once wide awake and roaring. The theory is compelling. The same colossal collision that sent shockwaves through the galaxy's outer gas would have also sent immense tidal forces rippling inward, violently stirring the material near the core. This could have funneled vast reservoirs of gas and dust directly toward the black hole's event horizon, fueling a brilliant and energetic outburst. For a cosmic moment, the cartwheel's heart might have blazed as an active galactic nucleus, one of the universe's most powerful engines, with jets of plasma shooting out at near light speed and a disk of infalling material glowing hotter than a billion suns. So where are the scars of that ancient feast? The search focuses on relics, enormous structures that outlived the active phase by millions of years. Astronomers look for faint, balloon-like lobes of radio emission floating far out in the galaxy's halo, the faded remnants of those once powerful jets. They scan for giant, bubble-shaped cavities in the hot gas around the core, carved out by the energetic outflows and now slowly refilling. Finding such fossils would be a profound and strange discovery. It would tell a complete story of galactic violence, from the initial impact that woke the monster, to its furious but brief feeding frenzy, to its subsequent return to slumber once the incoming gas was either consumed or blown away. The cartwheel would then be more than a beautiful ring. It would be a cosmic clock, its quiet center marking the time since the last great quake that shook it from within. This faint infrared haze could be more than just a galactic shroud. The collision's violence may have done something far more permanent, blasting a significant portion of the cartwheel's own substance out into the endless black. We are talking about the possibility that the galaxy is actively bleeding its star-forming fuel, enriching the vast and mostly empty space between galaxies, known as the intergalactic medium. This is not a gentle leak but a catastrophic expulsion. When the smaller galaxy punched through, the gravitational forces involved were so titanic they could have acted like a cosmic slingshot, hurling enormous clouds of hydrogen gas and dust out at speeds exceeding the galaxy's own escape velocity. Once that material crosses that threshold, there is no coming back. It leaves the galaxy's gravitational embrace forever, destined to drift in the lonely intergalactic void. Searching for this ejected material is the ultimate forensic exercise, like looking for cosmic smoke from a gun that fired hundreds of millions of years ago. Astronomers hunt for it by looking for the faint, telltale glow of ionized hydrogen, or by searching for subtle absorption lines in the light of distant quasars shining through the region, hoping to catch a spectral fingerprint of the cartwheel's lost gas. If they find it, the implications are profound. It means the galaxy is not just recovering, it is permanently diminished. The raw material for future generations of stars is being lost to the void, potentially cutting its star-forming future short. This ejected cloud would be a direct physical testament to the impact's absolute violence, a ghostly monument to the moment the Cartwheel's fate was irrevocably changed. It also reshapes our understanding of the cosmic ecosystem. We often think of galaxies as isolated islands, but events like this prove they are connected, that titanic collisions can seed the barren intergalactic medium with the very elements needed for future cosmic structures, spreading the ingredients for life far beyond their original homes. The missing radio whisper from the Cartwheel points to a deeper, more energetic mystery. All those supernova explosions in the starburst ring are more than just brilliant flashes of light. They are nature's most powerful particle accelerators. Each detonation sends a storm of subatomic fragments, protons and electrons, hurtling into space at nearly the speed of light. These are cosmic rays, and they are the key to the radio silence. As these charged particles spiral through the galaxy's magnetic fields, they should emit the very radio waves we find so strangely faint. So why is the signal so weak? The answer may lie in how the Cartwheel's extreme environment is changing the rules of acceleration. In a normal galaxy, cosmic rays bounce around in the turbulent magnetic fields near their parent supernova, gaining energy bit by bit like a pinball. But here, the conditions are anything but normal. The ring is packed with supernova, and their shockwaves may be colliding and merging, creating vast, unified fronts of energy. A cosmic ray particle might get a single, monstrous kick from one of these merged super shockwaves, propelling it to incredible energies far more efficiently. Once accelerated to such extreme levels, these particles could behave differently. They might punch straight through the local magnetic fields instead of spiraling tightly within them, escaping the ring before they have a chance to produce the expected radio glow. Or perhaps the magnetic fields themselves, stretched into those orderly radial spokes, act like cosmic escape tunnels, funneling the high-energy particles out of the galaxy with ruthless efficiency. The Cartwheel is not just a beautiful ring of stars, it is a colossal natural particle physics experiment, showing us a new and violent method of cosmic ray production that our quieter galactic neighborhood could never replicate. Pinpointing the exact moment of that ancient catastrophe is a scientific debate with no easy answer. The Cartwheel's collision did not happen in human history or even during the age of dinosaurs on Earth. It occurred in a deep cosmic past so vast that our best estimates span an enormous window, from perhaps 200 million years ago to over 1 billion. That is a difference of 800 million years, a timescale longer than the entire history of complex life on our planet. So why is it so hard to date this galactic car crash? Astronomers use different clocks, and each one seems to tell a slightly different time. One method involves playing the movie of the collision in reverse. By measuring the current size of the ring and the speed at which its material is still expanding outward, scientists can calculate backwards to estimate when the shockwave began its journey from the center. Think of it like finding an inflating balloon and knowing how fast air is being pumped in, trying to calculate when the inflation started. This method tends to give a younger age, often in the range of a few 100 million years. But another, very different clock looks at the stars themselves. By analyzing the light from the oldest stellar populations in the galaxy's displaced core and inner regions, astronomers can determine their ages. These stars, the survivors from before the crash, set a firm minimum age for the galaxy itself. The collision must be younger than they are. Yet the oldest stars in those regions can be billions of years old, which only tells us the event happened sometime after that. A more precise stellar clock looks at the brilliant blue stars in the ring itself. Massive, hot stars have very short lifetimes, burning out in just tens of millions of years. The fact that we still see so many of them blazing away means the starburst that created them must be relatively recent on a cosmic scale, or else they would have all exploded by now. This also points toward a younger collision age. So why do some models still suggest it could be over 1 billion years old? The complexity of the physics is the culprit. The expansion of the ring may not have been a simple, constant speed. It could have slowed down over time as it plowed through the galaxy's halo of gas and dark matter. The star formation in the ring might not have been a single, instantaneous burst, but a wave that has reignited in some areas, making the stellar populations appear younger than the event that started it all. Each method relies on assumptions, and in the chaotic aftermath of a head-on galactic collision, those assumptions can be treacherous. Resolving this chronological mystery is not just about putting a date on a past event. It is the key to the galaxy's entire life story. If the collision was very recent, say 200 million years ago, then the cartwheel is a fleeting spectacle, a brilliant flash in cosmic time that we are lucky to witness. Its structure is still violently evolving, and its future is highly uncertain. If the crash happened closer to 1 billion years ago, then this magnificent ring is a surprisingly stable and long-lived structure. It has already survived for eons, suggesting it might persist for billions more, becoming a permanent feature of this galactic group. The debate over its age is ultimately a debate about its nature and its destiny, forcing us to question whether we are seeing a momentary cosmic firework or the birth of an entirely new and enduring kind of galaxy. These stellar monsters may not even die like ordinary stars. The cartwheel's extreme environment could be forging the ultimate cosmic fireworks, a new class of hypernova so powerful it challenges our understanding of stellar death itself. When a truly massive star, many dozens of times heavier than our Sun, reaches the end of its brief life, its core collapses. In a typical galaxy, this often results in a supernova, a brilliant explosion that leaves behind a neutron star or a black hole. But here, in the pressure cooker of the starburst ring, the stars being born might be so colossal, so packed with nuclear fuel, that their final moments cross into uncharted territory. This is the realm of the candidate hypernova, a theoretical explosion orders of magnitude more energetic than a standard supernova. Its power comes from a different engine. Instead of a core collapse leading to a rebound shockwave, the core of these extreme stars might collapse directly into a black hole with such speed and violence that it triggers jets of material shooting out from its poles at nearly the speed of light. These jets, focused and unimaginably energetic, would bore through the dying star and erupt into space, beaming gamma rays across the universe. A hypernova would not be a symmetrical blast, but a directed eruption, a cosmic lighthouse of pure destruction. If such events are happening in the cartwheel, they would be the ultimate expression of its chaotic nature. They would forge and scatter heavy elements like gold and uranium far more efficiently than ordinary supernova, seeding the future galaxy with rare metals. They might also be the elusive progenitors of the longest, most powerful bursts of gamma rays ever detected, connecting this beautiful, wounded galaxy to some of the most violent flashes in the distant cosmos. This invisible magnetic maze holds the secret to the galaxy's strange silence. To map it, astronomers turn to a subtle property of light called polarization. When radio waves travel through space threaded by magnetic fields, their orientation can become aligned or polarized like sunlight glinting off the surface of a lake. By carefully measuring this polarized radio glow from the cartwheel, scientists can trace the invisible lines of magnetic force woven through its chaos. What they expect to find is a turbulent, scrambled field. The furious starburst, with its countless supernova, should act like a million mixers churning the galaxy's magnetic architecture into a chaotic, knotted mess. Yet the hints we have suggest something more complex and strangely beautiful. There are tantalizing clues that within the turmoil, a larger, more ordered structure might be emerging. Imagine a hurricane, a system of immense chaos, yet within it, the overall rotation creates a distinct circular pattern. The collision and the resulting ring of star formation might be doing something similar to the magnetic field, organizing the chaos into a coherent shape on a vast scale. This could manifest as a magnetic field that aligns with the galaxy's radial spokes, or one that traces the circumference of the ring itself. Such an ordered field would be a powerful, invisible hand guiding the galaxy's evolution. It could act like a cosmic rail system, channeling flows of gas along specific paths, either funneling material inward to feed the quiet core or efficiently venting cosmic rays outward into space, which would explain the missing radio emission. It could even influence where and how the giant molecular clouds collapse, making star formation more efficient in some regions and suppressing it in others. Deciphering this magnetic blueprint is perhaps the greatest observational challenge on this list, because the signals are incredibly faint and the geometry is so complex. But if we could see it, this invisible maze would be the master key, unlocking the connections between the galaxy's turbulent motion, its unusual chemistry, and its haunting quiet. It is the hidden wiring behind the entire magnificent, malfunctioning machine. Sculpted by those same gravitational tides, the Cartwheel's drama may be giving birth to entirely new worlds. Look closely at the faint, arcing streams of stars and gas that stretch away from the galaxy's main body, its tidal tails. Nestled within those streams, like dewdrops forming on a spider's web, are small, dense knots of light. These are not random clumps, they are candidate tidal dwarf galaxies, and their existence would turn a story of destruction into one of unexpected creation. We are used to thinking of galaxies as ancient things, forming billions of years ago from the slow collapse of pristine primordial gas. But these potential objects are different. They are being built right now in real time from the wreckage of the collision. The immense gravitational forces that stretched the Cartwheel and its companions also pulled out vast ribbons of gas, dust, and stars. Within those ribbons, pockets of material can become dense enough for their own gravity to take over. They begin to collapse in on themselves, forming a self-contained, gravitationally bound island of recycled cosmic stuff. Think of it as cosmic scrapbooking. The collision took pieces from the original galaxies, shredded them, and now gravity is stitching some of those pieces back together into entirely new, smaller books. Each of these candidate tidal dwarfs would be a galaxy in its own right, but with a bizarre origin story. They would be made not from the virgin hydrogen of the early universe, but from material already enriched by generations of stars, gas already laced with elements like carbon, oxygen, and iron. This means any planets that might one day form within them would be born with a head start, their cosmic chemistry pre-loaded with the ingredients for complexity. Their formation is a direct test of our ideas. Can a stable, long-lived galaxy truly be born from the debris of a crash, or are these just temporary mirages, destined to be pulled apart or swallowed back up in the next gravitational encounter? Finding and confirming even one true tidal dwarf galaxy here would prove that galactic collisions are not just destructive, they are generative on the most profound scale, capable of seeding entirely new island universes from the ashes of the old. That furious creation in the ring contains the seeds of its own destruction. This is the cosmic paradox of feedback, a process where the very stars a galaxy makes begin to shut down the factory that built them. In the Cartwheel, this self-regulatory mechanism is not a gentle tap on the brakes. It is a potential stampede toward a sudden and permanent silence. To understand it, picture a vast forest where every new tree instantly bursts into flame. The heat and wind from those fires blow the seeds and soil needed to grow the next generation far away, leaving behind only scorched earth. That is feedback in a starburst galaxy. The first stage is stellar winds. Those massive blue hot stars born in the ring do not shine placidly, they rage. Their intense radiation and powerful magnetic fields drive supersonic gales of charged particles from their surfaces, hurricane-force winds on a stellar scale that blast outward for light years. These winds collide with the surrounding gas, pushing it, heating it, and carving vast cavities, but the real demolition crew arrives with the supernova. When these short-lived giants finally explode, they do more than just flash brilliantly. Each detonation unleashes a shockwave of unimaginable energy, equivalent to the output of 1 billion suns, that slams into the galactic environment. This shockwave does two destructive things at once. First, it violently heats the remaining cold gas clouds, the raw fuel for future stars, making them so hot and turbulent they cannot easily collapse under gravity. Second, and more decisively, it can simply blow that gas clean out of the star-forming region entirely, hurling it back into the inner galaxy or even ejecting it into intergalactic space forever. In a normal galaxy, this feedback is a balancing act, a way to prevent star formation from running away and consuming all the fuel at once. But in the Cartwheel, everything is amplified. The ring is packed with supernova, likely going off in waves. Their combined shock waves could be merging into a single, continuous wall of pressure, a feedback front of unprecedented power sweeping through the ring. This could be clearing out the star-forming gas with terrifying efficiency, not in billions of years, but in a cosmically brief span of perhaps a few tens of millions of years. The galaxy might be strangling its own glorious ring of fire in a rapid, self-inflicted quenching. The strange and crucial lesson here is that the most spectacular eras of creation in the universe are often the most fleeting, because the engines of birth are also instruments of sudden, decisive death. The Cartwheel's violent beauty is not a permanent state, but a cosmic snapshot. We are witnessing a fleeting, brilliant phase in the life story of a galaxy, a chapter so brief that catching it feels like stumbling upon a photograph of lightning mid-strike. Most large galaxies, including our own Milky Way, have been shaped by collisions and mergers throughout cosmic history. These events are the architects of the universe, building giant ellipticals from the wreckage of spirals and triggering waves of starbirth. Yet the precise, perfect ring structure of the Cartwheel is a rarity. It represents a specific, transient moment in that violent process, a delicate balance of forces that cannot last. The initial shockwave has expanded, the ring of fire has ignited, but the system has not yet had time to settle into a new, stable form. It is caught between the catastrophe and the calm, giving us a front-row seat to the mechanics of galactic evolution in real time, or rather, in deep time. Its strangeness is the key. Every anomaly, from the faint spokes to the missing radio whisper, is a direct clue to the physical processes that govern how galaxies live and die. We are not just looking at a single oddball galaxy. We are looking at a universal principle caught in a momentary, magnificent pose. This snapshot teaches us that the calm, majestic spirals we often picture as the ideal galaxy are merely one frame in a much more turbulent and dynamic movie. They are the quiet aftermath of their own ancient violence. Their serene shapes the healed scars of past collisions we can no longer see. The Cartwheel, in all its chaotic glory, shows us the raw, creative fury that forges those familiar shapes, a fleeting glimpse of the universe in its workshop, hammering a galaxy into a new form right before our eyes. But the final, and perhaps greatest, mystery of the Cartwheel Galaxy is the one we have yet to solve. Its strangest discoveries may still be waiting, hidden in wavelengths of light we cannot yet see or in details too faint for our current eyes. The next generation of cosmic observatories is poised to turn this beautiful enigma into a detailed laboratory. The James Webb Space Telescope, with its piercing infrared vision, will peer through the dusty veil of the starburst ring like never before. It could resolve individual stars within those brilliant superstar clusters, telling us exactly how many there are and what they are made of. It might even detect the faint, telltale signatures of complex organic molecules swirling in the ring's gas, the probiotic building blocks that, in quieter places, could one day lead to life. On the ground, the colossal Square Kilometre Array radio telescope will listen with unprecedented sensitivity. It could finally map the galaxy's elusive magnetic field in its entirety, tracing the invisible maze that channels its energy and particles. It might detect the faintest whispers of the galaxy's lost gas, painting a complete picture of what was ejected into the void. And by measuring the subtle gravitational distortions across the entire system, it could chart the true distribution of dark matter, revealing the shape of the ghostly halo that holds this entire wreck together. Each of these future observations is a key to a locked door. They will not just provide answers, they will undoubtedly ask new, more profound questions we cannot yet conceive. The Cartwheel story, a saga that began with a cataclysmic impact hundreds of millions of years ago, is far from over. We are merely reading its latest chapter, and the most revealing pages are still to come. From the colossal collision that forged its ring of fire to the ghostly whispers of its missing radio signal, these 25 strange discoveries paint a portrait of a galaxy that defies every expectation. We have navigated its turbulent spokes, stood before the blinding glare of its ultra-luminous X-ray sources, and traced the invisible scaffold of its dark matter halo. We have watched as stellar birth and violent death engage in a paradoxical dance of feedback, and wondered if new galaxies are being born from its tidal debris. Each mystery, from its unusual chemistry to its potential hypernova, is not an isolated oddity, but a single piece of a grander cosmic puzzle. In this way, the Cartwheel Galaxy is more than a distant spectacle. It is a Rosetta Stone for the universe. Its perfect, wounded ring holds the key to decoding the universal language of galaxy evolution, translating the violent grammar of collisions, starbirth, and magnetic chaos into a story we can finally begin to understand. It reminds us that the serene spirals we admire are often the calm after a storm we missed by eons. So as this journey concludes, we turn the question to you. Of all its strange and wondrous secrets, which one captured your imagination the most? Was it the silent, displaced heart, the possibility of intermediate black holes, or the faint infrared glow of its scattered dust? Let us know in the comments below, and if you crave more deep dives into the universe's greatest mysteries, be sure to subscribe. The cosmos is full of wheels still turning, waiting for their stories to be told.